Okay, so now we're moving on to 13.2, where we're solving trig equations that have multiple angles, meaning that where we see the input to this trig function, there's some constant that's being multiplied or divided by our input. So instead of just having t, now we have something like 3t as our input. So the first thing we'll do, same thing as in 13.1, we're going to isolate our trig function. So cosine 3t I want to isolate and get by itself on one side of the equation. So I'll simply add over 1 and then divide by 2. So I have cosine 3t equals 1/2. Now, for a moment, we're going to pretend that the 3 isn't there. Now, this isn't the problem that we have right now, but it'll help us figure out what we're supposed to do when we get to the problem where there's 3t in it. So in the problems that we had like this from 13.1, we could go to Desmos, and we're thinking, okay, what input could I plug into cosine that's going to give me an output of 1/2? So I go to Desmos, make a cosine function appear. If I have an output of 1/2, what inputs are going to give me that output? Now for this particular problem, I am only told to look at solutions or find the solutions on the interval from 0 to 2 pi. Closed at 0, open at 2 pi. So I'm going to erect some walls really quick. I'll put it x equals 0 and x equals 2 pi, and I'm only going to look for solutions that appear between the green and the purple lines. Okay, everything else I don't care about. So I see that there's some solutions here at pi over 3 and 5 pi over 3. So those are the inputs, or those are the angles, that if I plug them in, are going to give me an output of 1/2. Okay, so normally, when I was dealing with a problem like this from last week, I would say, okay, t, my input has to be pi over 3 and 5 pi over 3 in order to give me that output of 1/2. We're essentially going to do the same thing, but instead of there being a t now, and now that it's changed to 3t, so I'm going to erase this line, thinking now that since this whole thing is 3t, I'm going to set this equal to 3t instead of t. So in the problems we were looking at in 13.1, I would say that my input needs to be pi over 3 or 5 pi over 3. So I can plug both of these in for t, and it will give me an output of 1/2. Now the only thing that's going to change now that we're not working with this problem in red, but really with that line in black, is instead of putting t, I am now going to put that both of those solutions are equal to 3t. Okay, so it's the only difference now. I'm just including that 3 that's in front of the t. So that is equal to, so 3t is equal to pi over 3 and 5 pi over 3. So now all I'm going to do is simply solve this for t. So I'll divide both sides by 3, which is the same thing as multiplying by 1/3. So when I do that, 3's cancel, and I'm left with t is equal to pi over 9, and t is equal to 5 pi over 9. So now if I plug these solutions in for t into this equation, they would be solutions to this equation. So now I know if I replaced the t in this equation with either pi over 9 or 5 pi over 9, if I substitute those in for t, that would give me, once I multiplied it by 3, an output of 1/2. And I know that to be true because if I do pi over 9 multiplied by 3, well, that's just going to give me pi thirds, which I know is definitely going to give me an output of 1/2. And same thing here. If we multiply this by 3, it's going to make it turn into 5 pi over 3. So essentially we're taking our solutions and we're just setting that equal to whatever is in parentheses for our input for the trig function. So let's try that again with the next problem. So here I want to isolate my trig function, so I want to get tangent of x divided by 2 by itself. So I'm going to subtract 3 over to the other side, and then divide that by 3, which gives me the answer -1. So I can rewrite this as -1. Alright, going back to the unit circle, I'm once again just going to figure out what input is going to give me an output of -1. Okay, so I want my output now to be -1, and it looks like in between 0 and 2 pi, I'm getting the solutions 3 pi over 4 and 7 pi over 4. So what I'll do is take this pi over 2 and set that equal to those two solutions that I got from Desmos. So that's equal to 3 pi over 4. And I'll make another equation for my second solution, so x over 2 is once again equal to 7 pi over 4. Alright, and then now I'm solving for x, so I'm going to multiply both sides by 2, and that's going to leave me with, I can cross that out so that there's a 2 left there, 3 pi over 2. And once again multiply here, and I get 7 pi over 2 for my other solution. So if I plugged either of those in to this equation and divided it by 2, plug that into tangent, I would get an output of -1. So those are my two solutions. 3 pi over 2 and 7 pi over 2. Alright, and then we'll try one last one. This one, thankfully, our trig equation is already isolated. This is the input to our trig equation, so I'm just going to go to Desmos and figure out where I get an output of root 2 over 2 for my sine function. So there's sine, and it looks like I'm getting the solutions of pi over 4 and 3 pi over 4. I'll take, again, whatever's in parentheses, whatever I'm inputting into your trig function, and that's what I'm setting equal to those solutions. So I'm going to set that equal to pi over 4 in one equation, and make another equation for the other solution and set that equal. Alright, and then now I'm solving for x, so divide by 3, or in other words multiply by 1/3, and I get pi over 12. And for the other solutions, I see that 3 and 3 are like factors, so those cancel out, and I'm just left with pi over 4. So my two solutions are pi over 12 and pi over 4. So that's working with trig equations. We're also now going to be talking about how to evaluate the composition of inverse trig functions. So I see here for the first problem that I have the inverse sine of 5 over 13, and all of that is inside of this cosine function. So the first thing I'm going to remember is it's kind of like when you're doing a normal composition of functions. So if you remember back to Unit 1, you do the innermost function first. So I'm going to work on finding this part first, and then I'll use that to help me find the outer part next. Okay? But start on the inside first. So I want to look at the inverse sine 5 over 13. What does this even mean? Okay. Well, I know that for a normal trig function, so just pretend this was sine, I usually plug in an angle, and then I get an output of two sides. For an inverse one, the input and the output are switched around. So now I'm putting in the ratio of two sides, and I'm going to expect to get out an angle. So from this, I should be getting out some angle. Don't know what it is right now, but whatever that angle is, I'm then going to take the cosine of that angle, and that should give me my final answer. Okay? So the first thing I want to try and figure out is which quadrant is that angle located in. Okay? So once I know that, that's going to give me a clue as to what the cosine of that angle is. Now for this, we're not even actually going to specifically find out how many degrees or radians that angle is. it's actually going to be unnecessary to solve this problem. All I need to know is which quadrant it's in. So I'm going to start by drawing my quadrants, and then remembering this little acronym, all students take calculus. Okay, so if you remember from before, this tells us which trig functions are positive depending on the quadrant that they're in. So I can look at the inverse sign 5 over 13. The first thing I notice is that the ratio of the two sides that I'm given, so 5 over 13, this is positive. Okay, so I know that I'm looking for a quadrant where my triangle, the size of it, the sign of it, is positive. Okay, well, that can only happen in the first quadrant because all of the trig functions are positive there, and the second quadrant because the sine function is the only one that's positive in the second one. So the first quadrant or the second quadrant, it's one of those two. So it's not going to be the fourth one or the third one. So we can cross those out. Alright, what's going to narrow it down to one of the two is remembering the restrictions for our inverse trig functions. So if I'm thinking about sine or even tangent, they have the same restrictions. The angle I'm supposed to get for my answer is only going to be found in one of two quadrants. Either the first quadrant or the fourth quadrant. Or in other words, the restriction is from pi over 2 to negative pi over 2. So I'm only allowed to look for my angle in one of those two quadrants. Well, considering that I can't look in the fourth quadrant, I already crossed it off, it must be in the first quadrant then. So I've narrowed it down. I'm working in the first quadrant since it's not in the fourth. So I can then go ahead and draw a triangle in the first quadrant. So I'll go ahead and draw a right triangle. And then this angle here is going to be my theta. This is the angle that I'm going to have as my answer to this part. What I'm going to do after that is I'll label the triangle. So since this is sine, this should be opposite over hypotenuse. So according to that angle, opposite is going to be 5, and then the hypotenuse is going to be 13. Then by using the Pythagorean theorem, I can solve for this missing side, which should be 12. So now my triangle is all filled out, and now that it's filled out, I can actually go ahead and calculate the cosine of that angle. Again, without even knowing what the angle is specifically, I can look at this triangle and know, okay, the cosine is just going to be adjacent, which is 12, the adjacent side of that triangle over the hypotenuse. So this whole entire thing is just going to boil down to 12 over 13. That is the cosine of that angle. So a lot of this is just figuring out which quadrant you're working in with these. So let's go ahead and try that out with the next problem that we see here. This one is giving us the arc secant, and arc is just another way to say inverse, so this is the same thing as putting that -1 there, of square root of 5. Now here, we could actually change this so that it's written instead of secant as its reciprocal function, which is cosine. So I could actually write this instead as arc cosine, but if I'm going to do that, the input, or the square root of 5, has to be flipped around the other way. So I'm going to write this as 1 over root 5. Okay, so this whole thing I'm going to rewrite as arc cosine 1 over square root of 5. So let's rewrite this whole line here. So at this point, once again, I recognize that all of this is going to boil down to an angle. Then, whatever that angle is, I want to know what the cosine of that angle is, and that will be my final answer. So again, the first thing for us to do is to figure out which quadrant is this taking place in. The restrictions for inverse cosine are the first quadrant and the second quadrant. We're only allowed to look for our answer between 0 and pi. So right away I know I'm restricted to the first or the second quadrant. And once again, remember the acronym, all students take calculus. So since this is cosine, and it looks once again like the ratio of our sides are positive, I'm looking for a quadrant where cosine's positive, which is either the first quadrant or the fourth quadrant. So my answer must be in one of those two quadrants. So it's not going to be the second one or the third one. Then I'm going to recall the restriction for inverse cosine, because it's a little different than the restriction for sine and tangent. So for inverse cosine, I'm only allowed to find the answer, my angle, in the first quadrant or the second quadrant. So my restrictions are from 0 to pi. So since the second quadrant is already marked off, we know that's not going to be where we find our solution. The first quadrant must be it. So once again, we'll draw a triangle in the first quadrant, and that angle, that is our answer, is going to be located there. Then we can label the sides of our triangle. So cosine is adjacent over hypotenuse, so adjacent is 1. And the hypotenuse is square root of 5. Alright, at this point you can do the Pythagorean theorem. I do it and I find out the other side is 2. Okay, and then last but not least, I'm trying to find the cosine of that angle. So the cosine is just adjacent over hypotenuse. So if you can see what happened here, if we have a function, so we had cosine, and then we had its inverse, which is arc cosine. So those are inverses of each other. Inverses cancel out, and then we're just left with 1 square root of 5. It's kind of like having other inverse operations, like a negative and a positive. Those are inverse operations. They cancel each other out. Or multiplication and division. They're inverses, they cancel out. So 1 square root of 5 is our answer, or if we wanted to rationalize the denominator, we could write this as root 5 over 5. Okay, we'll try this 2 more times. So now let's look here. I know that's going to turn into an angle, and the first thing I need to do is figure out which quadrant that angle is located in. So I see the ratio of my two sides are once again positive, so I'm looking in the quadrants where tangent is positive, so that's the first quadrant and the third quadrant. Tangent is not positive in the second or the fourth quadrant. And then next, I think of inverse tangent and the restrictions that are on it. I can only find my answer in the first and the fourth quadrant. So since the fourth quadrant is crossed off, it looks like I am in the first quadrant and not the third. So here's our angle theta, and we can start labeling our triangle. So since tangent is opposite over adjacent, my opposite side is 3, my adjacent side is 4, and if I do the Pythagorean theorem, this side should be 5. So now the sine of that triangle, according to this angle, should be opposite over hypotenuse. So I should have 3 over 5 as my final answer to this whole thing. Alright, and then the very last problem. So once again, I'm thinking that this turns into an angle, and I want to find the cosecant of that angle. So this time, when I look at the ratio of my two sides, it's negative now. So I want to find a quadrant where tangent is negative. So that's definitely not going to be in the first quadrant, because all of them are positive. And it's definitely not going to be in the third quadrant because tangent's positive there, and I'm looking for some place where it's negative. So in the second or the fourth quadrant, tangent is negative in both of those places. And then lastly, I look at my restrictions for the inverse tangent function, and I'm only allowed to look in the first and the fourth quadrant. So since the first one's already crossed out, I know that I'm creating a triangle in the fourth quadrant. I'm not using the second one. So I can begin labeling the triangle. Tangent is opposite over adjacent, so the opposite side is 5, and the adjacent side is 12. Now notice that there's a negative there, so I have to pick which one is going to have the negative. So since 5 is going down, it's in the negative y direction. Our 5 should be negative, and 12, since it's in the positive x direction, that should be positive. Alright, once I do the Pythagorean theorem, I figure out that this missing side is 13. Okay, and then the cosecant of that triangle, well, I recall that cosecant has a reciprocal of sine. And I know that sine is opposite over hypotenuse, so cosecant is just going to be that fraction but flipped around the other way. So it should be hypotenuse over opposite. So the hypotenuse is 13 and the opposite side is -5. Is our final answer for number 4.